Hello, everyone. Welcome to the Dean's seminar today, next version of our Dean seminar series. I'm not the Dean, I'm the Deputy Dean, so I do the introduction in the place of Anne or Dean today. But before we start, I would like to acknowledge that we are meeting today on one of the Monash campuses that are on the land of the Wurundjeri and Bunurong people of the Kulin Nation. That's unceded land, and I would pay my respect to the Wurundjeri and Bunurong elders, past, present, and emerging. And it's my great honor today to welcome Willy Zwaenepoel. He is currently since quite a few years, I think, the Dean of the Faculty of Engineering at the University of Sydney, and he is an ACM Fellow, IEEE Fellow, Fellow of the ATSE. He has won quite a number of awards, some of them lifetime awards, which tells you quite a bit about the contributions to different areas that Willy has done. His research interests, quite modestly, show operating systems and distributed systems. So I think it's pretty much a bit of an understatement, but if you look at the breadth of the contributions, it fits into these two areas, and there's quite a few really interesting ones. So I would like to invite you to look at them if you're really interested in any of these areas. We will hear today about one particular research contribution. And thank you, Willy, for taking the time to join us for this seminar and give us a presentation.
Thank you for the very generous introduction, and thank you all for coming. So as was mentioned, I'm Dean of Engineering, which means that I'm largely a bureaucrat for most of the time, but occasionally I do some research still when my boss is not watching. I get to do some research in the area that I've been working on for a number of years is storage, and in particular software for storage systems. And that's what I'm going to be talking about today. So the title of the talk is Software for Fast Storage Hardware. There's really been sort of a tremendous change in the storage hardware scene over the last 10, 15 years, and this has really created a number of opportunities for good research in terms of how the software should be structured in the storage stack. Now, for those of you that are perhaps not familiar with storage, I'll go through a bit of an introduction about the changes that have happened, and then I'll explain how that triggers changes in the software and some of the work that we've done in that space ourselves. So the prelude evolution of the storage hardware over the last sort of decade. So this is the first sort of important thing that you need to know. Storage hardware has become a lot faster, and I really stress a lot faster. So if you look, say, 10, 15 years ago, you could get sort of 100 megabytes a second out of a hard disk. Now you're talking with the modern Intel SSDs, you're talking about 2 gigabytes per second. So you have a change of a factor of about 20 over the last 10 years. So this is really sort of an important change and easy to understand. Now, the second major change is perhaps a little more technical. So I don't know if you remember from your operating system classes, but they would always tell you sequential access is much faster than random access. And in the old days, with mechanical devices, that's obvious, right? If you go with a mechanical device from one place to the place next to it, that's going to be cheaper than going somewhere else on the disk. Now storage has become electronic, and that's no longer the case. And so I've sort of shown here on the old mechanical devices, you would have a bandwidth ratio of about 30 to 40 between sequential access and random access. On modern devices, that ratio is 1. The cost is the same of sequential or random access. So what is the problem here? And the thing that I'm going to be talking about, if you look at the storage software stacks that we're using, they've all been designed for old systems, for slow systems in which sequential access is much faster than random access. The trouble is that if you go to the new devices, that kind of software doesn't work very well anymore. So we really need new software, and I'll explain what I mean by doesn't work very well later in the talk. So, sorry. So, no, I went too fast, and I'm going the wrong direction. So I'm going to give two examples of this. I'm going to show, this applies to all storage stacks, whether it's relational databases or file systems. But in this talk, I'm just going to give two examples. I'm going to talk about key value stores, which are now the backbone of most internet services. And then I'm also going to talk about online transaction processing and online analytics processing as two examples of this evolution and how the software has to change. So Act 1, key value stores. So just to put everybody on the same page here, what is a key value store? Well, it can be many things, but the core of every key value store is the same. The basic sort of data item is a pair of a key and a value. And so the operations that you can do is you can write a key value pair, that's usually called a put. You put a key and a value, or you get the value of a key by a get operation. Those are sort of the basic equivalents of read and write in a file system. And then almost all of these systems also have a scan interface, which says, give me the key values of all the keys between kx and ky. So you can specify a range of keys, and then you get all the key value pairs for which the key falls in that range. So obviously, since I'm talking about storage, I'm talking about persistent key value stores that survive a crash or a failure that still have the data around. And I'm also restricting here things to single machine, although this can be applied to multiple machines as well. So like I said, this has really become the backbone of many, many internet services, the storage backbone of many, many interests. And there's a whole bunch of these systems around. They started at Google with Bigtable, but now there's a number of systems around that I've picked 4 out of here, because these are the 4 that I will use later on in the talk to compare what we've done to these systems. But sort of to explain the concepts, I'll use RocksDB as an example. So RocksDB is perhaps the most common key value store out there. It was done initially by Facebook, but it's an open source system. So that's what I'll use as an example, but basically applies to everything that I say. So I said in the beginning, if you go to this modern hardware, things don't work very well anymore. So question is, what do I mean by they don't work very well? And basically the answer is you don't get out of the device what you could hope to get out of the device. So if you do the following single experiment, you replace this disk by this disk, which is twice as fast, and by the way, also twice or 3 times as expensive, you would hope to get some performance benefit out of that, right? And this is easy to do. These things are pin compatible, so you can take one out, you can put the other one in, and you run RocksDB on top of it, and what you will see is exactly nothing. There's no gain there's very modest gain in performance. And you say, well, this is no good, because I have a device that cost me so much more, so much faster, and I get nothing out of this. And the question is, why is this so? And so for explaining that, we'll dive a little deeper into sort of the performance measurements. So this measurement here has time in this axis, in the x-axis, and has the application throughput in the other axis. And you can sort of, on the back of an envelope, compute what it should be, and it should be somewhere between 400 and 500K. But in practice, what you see, it's really, really poor. It's basically barely 100 kilobytes in a good moment. The other thing you see is there's this very funny behavior here, where occasionally it goes down to 0, which is also clearly not what you would hope for, right? So again, you say, well, why is this? So the next thing we'll look at to try to explain this is how much of the device are you actually using? This is at the application level. Now we're going to look at the actual device and see what the bandwidth is that we're using. And so you get the same sort of funny result here that, I mean, we know what the maximum bandwidth is of the device. It's 2 gigabytes per second. But if you look what we're actually getting, you see that it's an awful lot less. So on average, it's less than a factor of 2. It's almost a factor of 3 less. And then again, you see this funny behavior where the thing goes up and down. Although the input load is steady, the actual output performance that you get of it is sort of up and down. And you say, well, this is not a happy thing. So again, why is this? It still doesn't tell us why this is. So does anybody know why it is? Make a guess? No. It's a good guess. He said cache, but that's not what it is. It's not at all obvious, and it's sort of counter to any intuition that anybody has about how a storage system works. The answer is that the system is actually bottlenecked by the CPU. So it's no longer, and so again, if you're not working in storage, maybe this is sort of sounds okay, but if you work in storage systems, it's sort of a dramatic observation. It's always been gospel that the device is the bottleneck and the CPU is partially idle. Now we're in a situation where the device has become so fast that the CPU, well, the device has become so fast and the software is so clunky that the CPU has actually become the bottleneck and the device, you can't run it at full speed anymore. So this is sort of the key lesson. If there's anything you remember from the first part of this talk, please remember this. If you use old software like RocksDB, the CPU has actually become the bottleneck rather than the device. And it's sort of a double punch because the software uses a lot of CPU because it thinks the disk is slow, but the disk is actually fast. And so you're doing something to try to optimize something that doesn't need to be optimized. So the old software creates the bottleneck on the CPU rather than on the device. And so if you want to get the maximum out of the device, you must optimize for CPU usage, no longer for device utilization. And that's in the system that I will describe here in a second. So that's what we're doing. Is that clear so far? Because if you miss this, the rest is not going to make much sense. So, yeah?
On the mic.
Sure, because you mentioned that CPU is a bottleneck. So is it possible, like, for example, we add more CPUs on the single machine to like achieve expected I/O performance?
It's always possible, but for sort of reasonable configurations, you will run into the CPU being the bottleneck. Yes, it's always possible, but for reasonable configurations, the CPU will be the bottleneck. Yeah.
Sorry, thank you. As far as I know, in the last even 20 years ago, for some operating system, there was a mechanism which can link the hard disk to memory directly without a CPU. Sorry, I forgot the professional name of that. There is a mechanism for that.
Yeah.
In that case, the CPU may not be the bottleneck. Is that
Actually, it will be. I'll explain in a second why. I know what you're thinking of. You're thinking of DMA. It still is the problem. So let me go on and sort of explain why this is the problem. So this is going to get a little more technical. It's not too technical, but I hope you can follow. So this is basically how RocksDB works and why it creates all these problems. So let's look at what RocksDB does when it does a write. So the first thing it will do is it will write the data into a log. The second thing it will do is it will write the data into an ordered data structure in memory, which is called the mem table in RocksDB. So every time it writes to the log, and then it writes to this mem table, which is an ordered data structure, at some point, this mem table will get full. It will make it immutable, create a new mem table where it does its writes, but write the old one out to disk. So the line here, the horizontal line, is what separates memory and disk. Above the line is memory, below the line is disk. And then, of course, you cannot keep on writing, right? Eventually, you'll run out of space. So when you run out of space, you'll do something called compaction, which means that you take the values that are no longer accessible and you throw them away. So more than the technical details here, what is important is that you see how the old software tries to optimize for a slow disk where sequential is much faster than random. So writing to the backup log is a sequential operation. When you write to a log, it's sequential, so it's pretty fast. And then when you write the mem table, you sort of write a big chunk all at once. Rather than you could say, well, the simple thing here to do would be just every time you write, right? As a write comes in, you write it to disk. It would kill you on old software. You have to write sequentially, and you have to write few times, because otherwise your performance will go down incredibly. But all of the stuff takes time, so this basically repeats what was said on the previous slide. What conventional key value stores do, they write to a commit log, they batch for sequential writes, they keep an ordered in-memory data structure, they keep an ordered on-disk structure so that they can find things quickly. And this I didn't mention, but there's typically sort of one index for the entire key value store that's shared by all the worker threads. So now I'm going to sort of contrast that with what Kvel does, what the new system does. And the funny thing here is, and this was very hard when we wrote the paper here, basically the point of the paper is you don't need all this stuff. You throw all this stuff out. Usually when you write a paper, you say, I have this wonderful new idea that I add to the system. Here, the paper was, you throw all this old stuff out and it works much better. So what Kvel does is it has no commit log. It doesn't try to batch for sequentiality, because sequentiality doesn't gain you anything. It keeps no order on disk, and it has almost no shared data structures. The only thing it keeps is it keeps an ordered in-memory data structures to quickly find something. So I'll explain all of this in more detail, but the key message here is all this stuff, which takes a lot of CPU time, you don't need it, and you'll come out better. That's basically the message, the overall message here. So let me go into a little bit more detail here. So the first thing is, let's go through what a put does. Well, when a put happens, you just put it down on the disk. You know, you don't bother with commit logs, you don't bother with mem tables, you just put it down on the disk. And you do that in separate files according, these are called slabs, for those of you who know what that is, that sort of cater to different sizes of values. So that's the first thing. The second thing is, how do you find something once you've put it on disk? And the answer is here, you keep in memory basically an index, a tree of some sort, the prefix tree as it is, that points to where that value is on disk. Third thing is, remember I said no shared data structures. So in a traditional file system and in a traditional key value store, there's one data structure that's shared by all the worker threads. So the index is shared by everybody. And so you have to have locking and whatnot to make sure that things don't get out of sync. So what we're going to do here is we're going to essentially shard the key space over different workers, and each one of them is going to have its complete own separate system, almost. So it has its own index, its own files on disk, completely separate from anybody else, which has the big advantage, of course, of no locking, which, again, we're talking about optimizing for the CPU, so no locking is a big gain. And finally, again, if you listened when you were taking operating systems, they probably told you something like this. You know, they said, if you try to write to the disk, you're going to write to the cache, to the page cache. And then this thing here is way too slow. So we're immediately going to tell the user, we've done it, although it's not really on disk yet. It's a bit cheating, but that's how things are done. Well, the thing is, this thing is now so fast that there's no reason to do this anymore. So you still have a page cache as before, that's always good, but you immediately write down to the disk and then you tell the user it's done. And again, in sort of traditional systems, that wouldn't work. But here, this thing has become so fast that it's actually faster to do this than to do this. And remember, I still need to pick up this right when the disk finally tells me, and so forth and so forth. So this is just, there's more changes to the system than this. This is just to get you a flavor of how the system works. And it's basically throwing out a lot of the stuff that was there before. So there's a few details. I don't want to get into much detail about them, but just again to give you a flavor of how these systems work. In a traditional file system, you don't worry about the cost of a system call. A system call is just in the noise compared to accessing the disk. Nobody ever worries about it. Here, the system call actually becomes sort of comparable in cost to a disk access. So you have to be very careful not to do too many of them, or you'll pay the price in performance. Just as an example of the kind of things that you have to worry about. Again, it's all about the CPU and maximizing the use of the CPU. So let me show you a few results here. So this is the machine. It's a sort of classic Optane drive from Intel. And this is a classic benchmark, YCSB. It's used in all studies of key value stores. And so I'm going to show our performance compared to these 4 other systems that I mentioned before. So here it is. And so otherwise I wouldn't talk about it. It's fantastic, right? I mean, we're the green one and everybody else is in gray. And you can basically see that so YCSB has different benchmarks depending on what the read-write ratios are. So some are completely read, some are half read-write, there's sort of various combinations. But you see that no matter what combination, we're doing a lot better. And that's the basic message here. The basic reason behind it is that we now run at disk bandwidth, that the CPU is no longer the bottleneck. We run at disk bandwidth, and so we run much, much faster than before. Okay, one final thing on this. Don't you see something funny about this graph? No? Yes? There is something funny.
Like it seems to be mute or...
There's something missing here, right? There's A, B, C, D, and F. You say, well, where did E go? You know, was he trying to hide something? And the answer is yes, but here is the result. So this is the same graph as you saw before with the different systems, but now for the E benchmark, which is mostly scans. And so here you see that the performance is comparable to RocksDB. And the reason is scans are the worst case for our system, because before you would put data next to each other. So if you have multiple items fitting into a block, if you read one block, you get them all. Here we're spreading them out all over. So I have to do multiple reads to get these blocks off the disk. Now, fact remains that the software is so much faster that the result is almost the same. It's not better, but it's almost the same. And in fact, it is better if you now look at the performance over time. You see that the green one is Quell, the gray one is RocksDB. You see that RocksDB again has this very variable behavior, whereas we are stable. The answer is that the RocksDB performance is so unstable because of this compaction thing. Compaction is basically like garbage collection, which if it kicks in, it stops the machine. And so you see that the performance here, when a major garbage collection kicks in, you go down to 0. We never have to do garbage collection, so we stay pretty much flat throughout. So average, we're about the same, but sort of performance-wise, we're, you know, or at least stability-wise of performance, we're doing a lot better. Okay, let me just to end this part of the talk, sort of restate the key lessons. The old software causes the CPU to be the bottleneck. So, because it's meant for slow devices and the device is now fast. And so the solution is that you have to optimize for CPU utilization. And again, for those of you not familiar with storage software and storage software research, this is a complete paradigm shift. It's always been the case that the device was the bottleneck, never the CPU. So let me perhaps open up for questions here, because then we'll go to the next thing. Yes?
I'll ask a question on the previous slides, because you said that in E, so you have the comparable performance with RocksDB.
Right.
But in the design, actually, you already have like a index, right? And also you have this partition. So it's supposed to support like scanning queries within a range, because you already have the index, prefix index.
Right.
So why here is still like a random access?
Okay, the index is in memory.
Yes.
But the data is on the disk.
Okay.
And the data is stored randomly. Okay. So the index is in place. That's not where the bottleneck is. It's going to the disk.
I see. Thank you for that.
Other questions at this point? Yeah.
So with this high speed, with the disk access, how does it now compare with memory access?
Okay, that's a good question. So his question is, how does disk access compare to memory access? It's slow. It's still quite a bit slower than accessing memory. And the other thing not to forget is that this is still a block device. So you have to read the whole block of the disk, whereas memory you can access word by word. So there's still fundamental differences.
How big are the blocks?
In this case, 4 kilobytes.
Thanks.
Other questions?
We do have a few that have come in through our online as well.
Okay.
So to start, does RocksDB write to a raw HDD SSD or to a file system on the storage device?
It typically writes to a file system. Yes.
Next one is, one of the justifications for commit logs and other memory structures mirrored to disk was to handle power failures so that volatile data is protected. How is this addressed in KVEL?
Excellent question. So I'm going to go back a little here. The commit log is there to save the system in this time of vulnerability between you've told the user that the stuff is there, but it's not there. But you've written it to the commit log, so later you can recover it. We don't need a commit log here anymore because we write it straight through to disk. And the other part of your question is, if you keep this in memory, what happens if you crash? Well, the answer is you rebuild it. Now, again, on a conventional device, that would take minutes. On a device of this speed, this takes a few seconds. So you can actually afford to rebuild the whole index without too much penalty. I mean, most systems, when they reboot, it takes more than a few seconds typically. And of course, if it's a prepared shutdown, then what you can do is you can write the stuff to disk before you shut down the machine. Other questions?
We have a few active people, which is great online.
Okay.
So the next question, what's the cost for removing the commit log? Is there no transaction support?
The answer is no, there is no transaction support in this system. This is a pure one write at a time system. That is correct, yes. So if you were to want to implement transactions, you would have to reintroduce the commit log. That's correct, yeah.
And so the next one, have you tried the performance of KVEL on an older slow disk?
Yes, very good, all the good questions. The answer is, it depends how old the disk is, basically. If you have a really old disk, KVEL will be slower than RocksDB because the penalty for random access then becomes very, very high. But on sort of previous generation SSDs were already better, and certainly on this generation SSD were better.
So the next one, do you get hardware contention, e.g. bus to or from the CPU and memory disk that impacts performance?
You really have all the good questions. I didn't go into this, but you see that it says here, manage the queue length. This is exactly to address the problem that was mentioned. So these devices are very fickle. Usually fast devices are always very fickle, and this is no different. So you cannot go to the disk with every single request, because then you will not get the full bandwidth. You have to build up a queue and then dump the whole bunch of them. But if the queue becomes too big, your latency will go up because a new one will get at the end of the queue and have to wait a long time. So you have to carefully manage the disk length so that you both get good bandwidth and good latency at the same time. This is a tricky part of the implementation, yes.
And the next one, can the device host a surrogate CPU of its own?
Not this device for sure. So there is a lot of work on sort of the in-storage processing, but that was not available to us.
And we'll go with one last one here.
Okay.
I have benchmarked a lot of SSDs with UFS/FFS, and many perform poorly on large bust sequential writes of blocks. Nothing like a top-end Optane. Have you tested KVEL on lower performing SSDs, especially those with lame caches on the SSDs?
Yes, and the benefits start disappearing. So the previous generation, it still works well, but then the older SSD generations, you start losing compared to RocksDB. And it's for the reasons that are mentioned there. Okay, I think we need to move on, or otherwise we'll be here for a long time, which is probably not what you had intended. So let me talk about the second part of the talk, which is OLTP OLAP systems. So what goes on here? A lot of systems, a lot of data systems have sort of two kinds of operations on them. So there's sort of OLAP, which is analytic processing. The AP stands for analytic processing. And these are basically long read-only transactions. For instance, this would be something like read the balances in all the accounts in the bank. And then you have OLTP, which are short update transactions, which just say change, transfer this much from this account to this account. Historically, those have always been run on separate systems, but more and more people want to run them on the same piece of hardware for two reasons. First of all, data is becoming bigger, and having two systems is more and more expensive. And then secondly, people really want to run analytic processing on fresh data. And if you have to copy it from one system to another, you typically would only do it overnight. And so this is not really fresh data, whereas people like to do it on fresh data. So how is this done? It's typically done by an isolation method, which is called snapshot isolation. And so the way it works is every time you write, you don't overwrite the old version, you create a new version. And you keep multiple versions over time. And then you give each version a timestamp. So you say like, this one's 15, this one's 16, this one, so forth. When you start a read-only transaction, you say it's now time 15, and I will see all the versions smaller than 15. So let me show you with an example, because I know this is a little complicated. So let's say that we have a database with 26 elements from A to Z, and our OLAP transaction you see there is reading the entire database from A to Z, and it runs at time 0. So it should read what's now in the database. Now comes along an update transaction that say wants to change D. So you're not going to overwrite D0, you're going to create a new version of it. So that the OLAP transaction can still read D0 if it later reads D. So this is a well-known, there's nothing new here. This is a very well-known method of doing things. Now, you do this on fast hardware. So let's say that what we're doing is we're running a scan like before, entire database, and then we have an update intensive workload that sort of keeps on changing things in the database. Does anybody see what's going to happen? The answer is major disaster, but the reason is why. And it's not at all obvious, I must say. I couldn't foresee it at all either. But the answer is you're going to run out of disk space. You're going to have what's called, with a technical term, massive space amplification, and you're going to run out of disk space. Now, why is that? And it's one of these things when somebody explains it to you, it's obvious, but I couldn't figure it out before I saw it either. So it's like this. Let's first return to old hardware. So this is a sequential operation, right? You just scan through the entire database. So it's sequential, so it's fast. These are random updates. It's random, so it's slow. So what's going to happen is very few new versions are going to be created. And so it's not going to be a problem. You can sort of garbage collect them over time. On new hardware, this is still fast, but the updates have now become very, very fast too. The fact that they're random doesn't slow them down. And so if for every update you create a new version, you're going to get a massive amount of new versions, and eventually you're going to run out of space. Is that clear? And it's as simple as you can, but I couldn't figure it out either. So again, let me sort of give you what is the key lesson here, sort of in the second part of this talk. The old software uses multi-versioning on the slow devices to get this snapshot behavior to happen. If you do that with a fast device, you're going to get massive numbers of versions, and eventually you're going to run out of space. And so you need to avoid this multi-versioning, and that's in the system that I am going to describe now. That's what we're doing. So the system is a layer on top of Kvel. It's called Kvel Plus that implements this. So the first question is keeping multiple versions, is it an inherent necessity or not? Can you really get away from it? And the answer is, in general, you do need, for a totally general scan and update, you need multiple versions. You cannot provide snapshot isolation otherwise. But for a very large class of analytics applications, you don't. And this class of applications we call commutative processing. What it does is, so the scan is as before, there's no restriction on the scan. It scans portions of the database or the entire database. But the following thing needs to be true. The scan, the output of the OLAP transaction must not be dependent on the order of the reads. And you must read each item exactly once. So before you could do whatever you want during the scan. Here we say it has to be commutative. The order in which you do it doesn't matter, and you can only read it once. Now, you think about it for a second. Most analytics processing are that, right? I mean, the example that I gave, if you just want the sum of all the bank accounts while you go through, it doesn't matter in which order you do it, and you read every element exactly once. Now, when that is true, you can play the following trick. It's sort of a cute trick. I'll explain it to you. So what we will do, same scenario, we're scanning the database in one application and we're writing D in the other one. So now we're not going to create multiple versions. We immediately going to install the new version, D1, in the database, and we remove the old version. Except that before removing it, we will hand it to the scan. And then the scan does the following. If you've read it already, you ignore it. If you haven't read it, you read it. If you read it later, again, it's a no-op, you know, because the version number has increased in the database and you will not see it. So I went through this a little quickly. Is this clear? Because this is the key idea. It basically relies, again, on the fact that you will read things only once and that the order doesn't matter. So if something comes in sort of asynchronously, you can read it and process it then, and the result will still be the same. Is it clear to everybody? Any questions? No? Okay. So once you do that, you don't have multiple versions in the database anymore, right? That's sort of the key goal here that we were trying to achieve. So let me perhaps skip this here a little bit in the interest of time. The relevant the more relevant thing here is that this commutative processing applies to all the things that you typically see in an analytics workload. You know, things like MapReduce, summing of elements in the database, group by. You always read things once and the order doesn't matter. So it's very, very broadly applicable. In fact, we looked at the TCP/C benchmark, which is the classic benchmark for analytics software, and there wasn't a single benchmark for which it didn't work. So it is really very broadly the case. So let me immediately go to the evaluation here. So the same hardware, same benchmark, except that the benchmark is now a little different. We will do one scan and one heavy update heavy workload. And we'll do the scan with what I call vanilla snapshot isolation here, the classic multi-version implementation, and then our system. And so again, otherwise I wouldn't be talking about this works like a charm. And of course, it's obvious that it works like a charm. It couldn't be any different. So this is time in the x-axis, and this is the number of old versions at any given point in the database. And so, well, unsurprisingly, since we never create new versions, it always stays at 0, whereas in classical snapshot isolation, it grows linearly as you progress. And at some point, you're out of disk and the whole thing crashes. So this is sort of the key result here, that you don't create any extra versions, but you get the same semantics. Now, you may wonder, yeah, that's all fine, but have you not slowed down the scan by sort of having to interrupt it every time a new value comes in? And the answer is no. In fact, the answer is to the contrary. It goes faster. And that is sort of an interesting point here. So again, this is the time axis in X. This is the throughput of the scan. How many elements can you scan per second? This is classical snapshot isolation. This is QuAL+, and you see that it can scan much faster. Now you say, well, why is that? That shouldn't be, because you're doing more work. The answer is actually, and this was again sort of a complete surprise to me when I saw it, because you're handing it to it, it's in memory. And so you read most of the scanned items out of memory rather than from the disk. So in classical snapshot isolation, you don't do anything sort of preemptively. You just wait until the scan comes and then you get it from the disk. Here you're sort of handing it to it, and so it's there in memory by the time you access it. So surprisingly, as a byproduct, it actually becomes faster for the scan at least. And the other question that you may ask is, doesn't it slow down the update? Because now you need to forward every time. And again, the answer is no, the performance of the two is about the same. So you can see here again, this is the performance of the update. The orange one is classical snapshot isolation. The black one is ours. And so you see that as long as the scan is running, the throughput is about the same. And then since we finish more quickly, we actually go up while the other one is still busy scanning. So again, I'm sort of going through this a little faster to keep us on time here, but the key message here is, again, let me repeat it. The old software uses multi-versioning, and you can do that when creating versions is very, very slow, which it is on old software. If you can now create versions very, very fast, you're going to create a problem with all these new versions. And so you need to find a solution that avoids this multi-versioning. So I have a final few slides, but let me stop here for a second and ask if there's questions about this part of the talk. Yes.
So one from our online audience. SSDs do internal garbage collection for wear leveling purposes. With large sequential snapshot writes and deletes on the SSD, have you observed any impacts on SSD performance?
Okay, it's somebody online must really know this stuff, because this is a very, very good question. So the answer is no, we haven't observed any effects. But I want to caution a little bit, reading too much in that conclusion. We haven't really run it so long in production that wearing out of the SSD might actually become a problem. So it is possible that over time this becomes a problem. Yes. Yeah. That's it. Okay. Any questions here? Okay, then let me finish up. So you may have wondered about, NVRAM is all the hot item, right? Why does he still, you know what NVRAM is, right? Non-volatile RAM, which is exactly what you were asking for. It's memory, but memory that is non-volatile, that doesn't go away. And so for a while, this was all the rage, and you might wonder why he's not talking about this. Well, so here's an example of NVRAM, and the only commercially available example. It's Intel PMEM. So again, just for the people that don't know, this is very different. This sits on the memory bus, not on the device bus like the SSDs that I talked about. It's byte addressable. You can read a byte at a time, not a block device where you need to read 4K. And then it's persistent, it keeps its content over a power failure. The other thing that's nice about it is it's denser than DRAM. So you can put more of it on a single DIMM, but it is slower, considerably slower. Not as slow as an SSD, not as slow as a disk, but nonetheless, consistently slower. So does anybody know what happened to this thing? No? So Intel killed this. So this wasn't exactly a very successful product of Intel. And you would think this is a fabulous idea, right? Memory that doesn't go away. How come this didn't sell? And there's a variety of reasons, but basically, we can turn off the recording here for a second. Intel screwed it up, so they made a number of egregious mistakes. So first they provided a software simulator, then it turned out that the software didn't match what the hardware that they provided later did. So too bad for the people that wrote papers based on the software simulator, but it's completely wrong. And then there were sort of significant flaws in the first generation hardware. The other thing that is a problem more from the commercial side, not so much from the technical side, is basically it was all proprietary, Intel only hardware, and people don't like that. People want a variety of suppliers, and so people were very reluctant about doing that. The other thing that sort of, I never thought about this until the thing sort of went down in flames, but there wasn't really a killer app. If you want to sell new hardware, you better have a killer app that people say, this is now going to be so much better. And the answer is, with a block device, if your data, sort of the basic size of your data item is larger than a block, well, you don't need this, right? Why would you want word level access if your data is at least as big as a block? You don't want all that mess, And so this stuff is fairly hard to program, because if you have a block device, it's very simple. The block is written or not written, period. There's no in between, no half-written blocks. If you're allowing word level access to a memory segment, then you have all the classical synchronization problems with failures, right? You update a linked list, you take the pointer away, the thing crashes, well, you've lost the rest of your list. And so the combination of these two, the fact that didn't seem to be really a whole lot of applications that needed this, and that it becomes hard to program, sort of really, sort of the thing had sort of lead in its wings from the start. Now, there may be an angle at this that is somewhat unexpected, but nonetheless very interesting. The killer app may not be where you think it is. And the killer app may not come about from the fact that it's persistent, but may come about from the fact that it's denser than DRAM and therefore cheaper. So if you go ask in Google or in Facebook, they'll tell you, well, maybe they'll tell you, but it's certainly true, that the main infrastructure cost of a data center right now is memory. That is the expensive part. The address spaces of modern apps have gotten very large. They need to be in memory, so you need to put a lot of memory on your machine. Memory has become expensive. So now if somebody comes along and says, here's memory, it's cheaper and denser, it's wonderful, right? It's exactly the solution to your problem. So I think this may actually be the future of these kinds of systems, where NVRAM is not used for its non-volatility, it's used as an extension of DRAM. And so the trouble with this is that it's slower and sort of slower in funny ways, but slower. So this is actually what we're working on now, is to sort of see how to deal with these funny characteristics, not with the goal of providing persistence, but with the goal of extension of DRAM. And so we'll have a paper coming up in a month or so at OSDI about this. So let me finish up here. Thank my collaborators. Oana Balma was my student at Sydney, is now an assistant professor at McGill. Baptiste was a research fellow at Sydney, is now at the University of Neuchâtel in Switzerland. And Karan Gupta is with Nutanix, the company I've worked with for a long time. Well, at the time we started, we were employee 4 and 5. Now he's the VP of engineering. The company has 6,000 people now. But we've always worked together on it's a storage company on these kinds of problems. So with that, let me sort of repeat the main message here. Hardware is changing. If you use conventional software on this new hardware, you're not going to get the benefits at all. I just gave you 2 examples, but many more exist. It applies to file systems. It applies to relational databases, any storage system. So we really need to change the software storage stack to get the best out of this new hardware. And that's it. I'll be happy to take more questions if more questions. Thank you. Thanks. Any more questions?
I think we're a bit running out of time, but maybe there's a couple of questions, quick questions. I don't know if someone here in the room or online.
There's just one that's come through online. What operating system support did Intel have for this NVRAM?
They use a library which is called PMDK, persistent memory. I don't know what the DK stands for anymore. Development kit, PMDK, persistent memory development kit. It's not operating system support per se, it's a library that you link in with your program. And that's how they imagined things would be used, which is probably was another mistake, because you do need operating system support to get the full benefit out of this. Yeah.
One question here.
Thank you so much. It was very interesting.
Thanks.
We are working with these small devices like Raspberry Pis and things
Yeah.
like that. Have you done any research on the storage that they are using, like SD-RAM or SD cards as well?
No, not really. I think that's really a different class of problem. This is really sort of oriented towards data centers and server-based systems, which have massive demands for throughput and latency, whereas what you're talking about is more about reliability and low power use and things like that. No, I haven't worked on that, no.
Really, you just mentioned that Intel has discontinued the production, and your paper is coming out now on this one. So I just wonder, what's the motivation behind of kind of working on this discontinued product?
It's a very good question. So the product may be discontinued, but well, two things. First thing, I think other vendors will eventually supply non-volatile RAM. Second thing is there's now a new development in the storage hardware world. It's called CXL, basically where you have storage with your CPU, but then you have remote storage as well that's accessible over a high-speed link, over a memory link. And so I think some of the ideas, maybe not all, will continue to apply there.
All right, thank you.
Okay.
Okay, thank you very much. I'm pretty sure that quite a few of our researchers can considerably slow that down with post-quantum cryptography and these kind of things, but security in that world is an interesting thing to look at. But anyway, thanks a lot for this excellent talk. I think it looked like people enjoyed that a lot, and thanks for taking the time to join us for that.
It's a pleasure.